Thank you so much for inviting me here. So I'm trading off my undergrad teaching for more interesting teaching. Good. Excellent. So yeah, Ollie told me that the audience is split roughly half and half pure people, half impure people like myself doing theoretical physics. I'll try my best to alienate both sides. So please, I'm gonna say a bunch of physics words. As Ollie said, do ask me more during the Q&A question. And I'm not gonna try to justify why do we do a few things. We do them because of physics, so please do ask. Although I said modular forms, actually most of the things I'm gonna say about are modular functions, but anyway, modular forms and AdS, CFT, and I'm not gonna tell you what AdS CFT is. I'm just gonna say a few words. Good, so I roughly divided my lecture. So today I'm gonna give you a little bit of an introduction to the type of quantities that we want to compute. And in particular, what Ollie already mentioned is n equal to 4 supersymmetry and Mills theory. And I'm gonna make it very concrete, again, because half of the audience are mathematicians, so I'm gonna give you a quantity that's gonna be some matrix model to compute. And out of this matrix model, we're gonna be deriving a lot of interesting modular functions. And in particular, I'm gonna be talking about two types of quantities. I'm going to introduce them already today, but then in lecture 2, I'm going to be talking about this first quantity, which is going to be something which is called an integrated correlator. And I'm going to show you that this object admits a fairly interesting lattice sum. It's actually pretty interesting. Samuel, I think you're Samuel, right? Very good. Nice to meet you. He's going to be talking about theta series. They're going to make an appearance in two different fashions in here. I thought, given the audience, especially for PhD students, I'm going to be talking about something particularly interesting from my point of view, which is an SL2Z spectral decomposition for this object. And then, for the second lecture, third lecture, actually, I'm going to be talking about a second quantity, which is a little bit harder. And this is going to give rise to some proper, well, sort of proper, theta lift of some objects. And for the people in the audience who know what I'm talking about, this is going to give rise to some objects which are called generalized Eisenstein series. Good. As Ollie said, please do interrupt me at any given time. So these are rough outline. So for today, I just want to say a few words for the physicist on why do we care about these objects, and then I'm going to define these objects. So first of all, the title, AdS CFT. So we are interested, so this is sometimes called the AdS CFT dictionary. We are interested in computing certain scattering processes of strings or gravitons in type 2B superstring theory on a 10-dimensional background given by AdS5 cross S5. This is something very difficult to do. You can ask Ollie all about it. If you try to push it at higher genus, there is some beautiful math, but it's actually something really difficult to do. And so we try to bypass entirely the problem and study something else. We can study n equal to 4 supersymmetric Young-Mills theory, which is the unique, maximally supersymmetric gauge theory in 4 space-time dimensions. And the idea that most of the things I'm going to define are going to be living in here, but then thanks to this dictionary, we can actually learn about stuff in type 2B, and the physics of this stuff, I'm not going to tell you about it. Again, question and answer session, please do ask me about. So living on this side, the data that we need to provide is actually fairly minimal. This is a gauge theory, so theory of some fiber bundles. You need to tell me the gauge group. And so for most of these talks, these lectures, the gauge group is going to be SUN. So there's just going to be some integer parameter here. That's the first thing. There are some beautiful structure going on if you don't assume SUN. Again, if you're interested, you can ask me about orthogonal groups, the sectional groups later on. But for these lectures, we're going to be sticking with SUN. So the first data you need to give me is an integer. And secondly, you need to give me what is called the Yang-Mills coupling, or complexified coupling, which, apologies for the mathematicians, I'm going to denote it as tau instead of z, is some number in the upper half plane. For the physicist, this is the topological angle plus 4 pi I over G Yang-Mills squared. H. I don't know why I'm writing it. You all know what it is. So the reason why we want to study z equal to 4 more in detail is the following fact. If you study certain quantities, which are called correlation functions, and you consider the rank of the gauge group N to be large, then these objects in here are related to scattering amplitudes in this holographic theory, in the holographic type 2B superstring. And again, for the physicist, the maps in parameters is if you take square root of G Yang-Mills square times the number of colors N, this is related to the size of AdS divided by alpha prime, the string length square. Yeah. No, it's a 4, exactly. So I'm using curly N. There is a very subtle difference. Curly N stays 4. Calligraphic, sorry, not calligraphic N. Straight N goes to infinity. Thank you. Yeah. Good. And tau in this case is related to really the string coupling, what is usually called the axiodilaton. So I'm now going to define some quantities living here, but what we really have in mind in here is computing scattering amplitudes in this dual. In here? Yeah. Very good. That's just because in type 2B you have a bunch of fields. There is also a pseudo-scalar, which might pick up a vev. The vev of that scalar is C0, which is precisely the analog of the axiom. Just like the theta angle, you see here the real part is theta, which is like the axiom. Yeah. Yeah, thank you. Most of the time, usually people forget about the real part, but what since in here you're really dealing with real analytics, so they're not holomorphic functions of tau, you're not really setting the theta angle to 0. There are two different things. You're either forgetting about the theta angle, which means you're projecting on the 0 mode with respect to some Fourier decomposition, or you're setting the theta angle to 0. These are two different things to do. Yeah. Normally, people just care about the imaginary part just because it's G string or it's G Yang-Mills on the dual theory. Yeah. So before defining the type of function we're interested in, I need to make a little comment about what is called n equal to 4 electromagnetic duality, which has extremely strong implication for the type of quantities we expect to find in this theory. So this is due to Olive and Montonen or Goddard, Newitz, and Olive. So the idea is that if you take this n equal to 4 super Yang-Mills theory with gauge group SUN and coupling constant tau, you compute some quantity in here This quantity should be dual. In many cases, this dual will mean it's going to be equal to the same quantity computed in the same theory, where the gauge group is the Langland dual of G. Let me not be super precise in here. I'm going to say the Langland duals of SUN is SUN. That is not true, but for everything I'm going to be saying is effectively true. And the coupling constant, you send it to your favorite SL to Z transformation. It's sometimes called electromagnetic duality. Again, for the physicists, if you have ever taken Maxwell equations in the vacuum, and you take the electric and magnetic field, and you do an SL to Z transformation, the Maxwell equations do not care in the slightest. So this is a supersymmetric version of electromagnetic duality. What it's going to mean for us is that most of the quantities I'm going to define in here will transform covariantly under this transformation. In particular, they will behave like modular functions. They will be invariant under the action of SL to Z. Good. So how do we access some of these quantities? And now I'm going to finally give you some concrete equations. We're going to be using this matrix model formulation. Again, this would probably deserve a lecture series on its own. I'm just going to give you the punchline. I'm very happy to give you more details in the Q&A session. But this is some beautiful construction due to Pestun. As physicists, we are perfectly fine with working with this path integral, no matter whether it's well-defined or not. But if you really want to get like some properly defined quantity, that's a terrible thing to do. But thanks to Pestun, this theory here actually admits not a path integral definition, but a matrix model definition. So the idea is to start with a different theory. So this is called n equal to 2 star. In terms of matter content, it's the same as n equal to 4. The only thing you do, you introduce a deformation parameter, which is going to be some real number m. Again, for the physicists, you're giving a mass m to some hypermultiplets. That's the only thing you're doing. But you're breaking the number of supersymmetries. So now you have reduced to 2 supersymmetries. This would actually allow us to get a little bit more freedom. So when m equal to 0, this n equal to 2 star theory reduces to n equal to 4. I'm now going to define something for you that is also a function of m, but at the end of the day, I'm going to be setting m to 0, so I'm going to be reading some quantity in n equal to 4. What is this quantity? This quantity, I can remove that, is the so-called partition function of n equal to 2 star on a 4 sphere. Let me write it out and then comment. Can I move this one? Yes. All right. All right. All right. Please let me know if you can't read what I'm writing. I need some more space. All right, let's write it here. Let me define a quantity that takes as an input an integer, a real parameter, and an upper half plane parameter, and spits out a real number. This is going to be the partition function as a function of the rank of the gauge group, this deformation parameter m and tau, and it's defined by the following integral. It's an integral over Rn, a measure that I'm going to be writing shortly in terms of A, e to the minus 2 pi tau 2, A inner product with A, times two objects. One which is called Z perturbative of N, M, and A, and the modulus square of what is called Nekrasov partition function. The function of N, M, tau, and the integration variables. So cutting a very long story very, very short, this ill-defined path integral of n equal to 2 star can actually be written as this matrix model integral. And now I'm going to define the whole set in here. But again, yes, please.
Too many n's.
Yeah.
Just some parameters.
The rank of the gauge group. Yeah. Yeah. Later on, so I'm going to say now a few things about n equal to 2, for example, SU2 gauge theory, which is like, let's say, a supersymmetric version of Yang-Mills SU2. But then later on, I'm also going to be studying, as I was saying here, the limit in which n goes to infinity. Yeah. And then, sorry, which other n is there? Yeah, so that's the first entry, an integer. Then the second is this deformation parameter, which eventually I'm going to be setting to 0. And lastly, tau, which is going to survive. That's going to be our modular parameter. Again, sorry? Yes. Tau is equal to tau 1 plus I tau 2. Cheers. Thank you. Yeah. So you can see immediately, that's a good point, that this object in here is not holomorphic in tau. This is going to be a real analytic function of tau. Good. So what are these symbols that I've introduced over there? It's going to take me a minute to clean the board, so if there are more questions, please do ask. I like the path integral, which is very ill-defined mathematically speaking. This matrix model is something that you can actually evaluate numerically if you so wish. But we're actually going to be doing some analytic calculations. Yes, exactly. I'm going to write it in a second. Yeah, thank you. Yeah, so A, again, from a physics point of view, this Pestun trick allows you to localize the path integral to a finite dimensional locus. A parameterizes the eigenvalues of some SUN Hermitian matrix. Yeah, that's the web of the scalar field in the joint. Good. Is it okay if I'm making such a mess, or is there any other smarter way to do it?
Well, I'm inclined to say it's available.
All right. Good. So what are all these quantities? So let's start with a measure that indeed, as anticipated. So A parameterizes the Cartan subalgebra of the gauge group, which in this case is SUN, which is a funny way of saying this is just a vector of n variables and real variables. And the measure is just the product. These m variables subject to the constraint that the sum of all these variables vanishes. And then you diagonalize a matrix, so you get the van der Monde determinant. So that's exactly what you were asking. So these are some eigenvalues of some n by n Hermitian matrix. Good. The exponent over there, what I denoted with the inner product of AA, is nothing but the Killing form, AI squared. So you see that that integral in there is some particular type of Gaussian integral. Yes, David? And then the two remaining things that you're integrating over. So what I denoted by Z perturbative is what in physics language is called the one-loop determinant, and is given by the following expression. It's a function of the number of colors, the deformation parameter, and the integration variables. In particular, it's not a function of the tau coupling, and it's given by the product of I less than j, h squared aij divided by h aij minus m h aij plus m, where aij is the difference in eigenvalues, and this h function is related to Barnes G function, exponential of minus gamma plus 1 x squared times g 1 plus ix g 1 minus ix. This is Euler-Mascheroni, and this is Barnes G function. Again, for the physicists, sorry, yeah. Very good question. I was going to say this comment right now. Thank you. So this is one of the beauty of this Pestun localization. So I can say some more details later on in the Q&A session, but basically the idea is that you deform slightly the path integral by introducing some supersymmetric invariant term. And when you send the deformation parameter to infinity, you will localize on a locus of fixed point, and the saddle point approximation becomes exact. Hence, you only stop at the one-loop determinant. Thank you. Yeah. This is the physics version of Distermann-Heckman localization formula. In general, you expect infinitely many loop corrections. In this case, the one-loop determinant is suffice. And lastly, for the last beast, which is what is called Nekrasov partition function. The Nekrasov partition function accommodates for what they're called instantons. So it takes this form. 1 plus the sum over all positive integers, q to the k, that k Nekrasov n m a. So q is the exponential of 2 pi I tau, which, again, for the physicist, this is the instanton action, exponential of minus 8 pi squared over g ambient squared plus I theta. So you see that due to these q to the 10 terms, this Nekrasov partition function, whatever it is going to contain corrections due to instantons. So again, going back to your question from before, sure, the one-loop determinant terminates, so that's the whole perturbative series, but we still receive an infinite number of non-perturbative corrections. And the k instanton sector, so sorry, in physics language, Z Nekrasov k is what we call the k instanton sector. Has two properties. So first of all, when I set this deformation parameter to 0, remember in here, I introduced a deformation parameter just to have a little bit of wiggle room. It's going to appear clear shortly. But when I set this parameter m to 0, I land on what I actually wanted to study, n equal to 4. And in this case, this partition function reduces to 1. And just to give you a little bit of an idea of what it looks like, the one instanton Nekrasov partition function takes this form, minus m squared, L1 to n, the product j different from L, ALJ plus I squared minus m squared divided by ALJ plus 2I. So this k instanton partition function is in general some rational functions of these integration variables. It can be defined quite beautifully in terms of Young tableaus. Let me not enter there. So bottom line is that quantity over there, which I defined, the S4 partition function for n equal to 4, is a particular complicated, but is a matrix model integral. So we can evaluate it. Yes, please. Yes, I is a complex unit. Yeah, this is why I use L and J instead of I. Thank you. Yeah. Excellent. Note, Paysoon also tells us something else. Good. Can you remind me, Ollie, what time am I due to finish, technically?
5 minutes.
10:45. Oh, that's great.
10:45.
Perfect. But that's with questions, right? I'll try to be conservative. Yeah. 1 hour plus. Perfect. Yeah. No, that's great. Yeah, I'm doing okay. Yeah, because I wanted to introduce something else. I'm not going to talk about it, but since people in the audience might be interested, I want to say a few words in here. So Paysoon also tells us how to compute something else. What is called the fundamental Wilson loop in n equal to 2 star. And again, for the physicists in the audience, this is the expectation value of the path order exponential of the gauge field. You take a great equator on S4 and you compute this expectation value. But again, just to give a matrix model formulation, this is a function that is a real, an integer, and an upper half plane, and spits out a real value. And it's given by a very similar matrix model. Pretty much identical. So all the pieces that I wrote over there are there. That perturbative, that Nekrasov squared. The only thing you do, you insert in the matrix model this quantity. 1 over n, the sum 1 to n, e to the 2 pi a I. Yes, please.
Promising you'll get real
It does not in here, but thanks to the fact that I put the modulus square, it does. Yeah. So that's a good point. Then Nekrasov is only like half of the instanton partition function because, of course, you expect instanton, instanton, anti-instanton, anti-instantons. So that Nekrasov is the holomorphic part, but in the path integral, you get the modulus square. So this is actually going to lead to, yeah. So you're going to get instantons, you're going to get anti-instantons, and you're going to get the product of the two. Yeah. And again, in particular, most or In the first courses on modular forms, normally one looks at holomorphic modular forms. In here, we're going to get real analytic forms. So, thank you. Yeah. Yes, please. Again, sorry? Yeah, very good. It's the great equator of S4. Yeah. So also I'm cheating in here. It's not just the integral of A. There is the supersymmetric completion. Yeah, that's a half VPS Wilson loop wrapping a great circle on S4. Thank you. Good. More questions? Good. So now, out of these two matrix models, we're going to be defining some quantities, and these are the quantities that we're going to be studying. They're going to be particular, real analytic modular functions. So let me keep both path integrals and just write them here. So the key point is this one. Using these two matrix models, 1 and 2, we can define certain integrated correlators in n equal to 4. So let me define them. C of n tau is defined as a quarter delta tau d2m log of z, m equal to 0. So delta tau is the SL2R invariant Laplacian on the upper half plane. And then I'm going to be defining h of n and tau as d4m log z, m equal to 0. And lastly, I'm going to be defining IW and tau as the 2 mass derivative of the log W object over there, m equal to 0. So we define these two integrals, and then we take a bunch of derivatives with respect to the parameters of these integrals. So first of all, let me go back to the comment I made before. This deformation parameter m was just to give us a little bit of freedom. I can take some derivative with respect to m, but at the end of the day, I'm setting this m to 0. So for the physicists, this, although I was starting in n equal to 2 star, since at the end of the day I'm setting m to 0, whatever these quantities are going to be observable in n equal to 4, which was the first thing I wanted to compute. Secondly, what are these quantities? Well, again, let me give some physics argument. I'm not going to enter the details, but for physicists, that's something that is pretty clear what to do. So suppose that I gave you a path integral. Note again that it's not a path integral, okay? This is a matrix model integral, so these quantities are well-defined mathematical objects. While instead the path integral arguably is not particularly well-defined. But for the sake of argument, let me say that I have a path integral. So suppose that I have a path integral, is some integral over some fields or some unspecified measure, some action of the fields phi, and then some deformation parameter, lambda, which is attached to some operator O. What does it happen if I compute d lambda of the logarithm of the partition function? Well, you see in here, I'm going to bring down whichever operator is attached. So this object will lead to some correlation function in which I'm inserting the integral over the space-time of the operator O attached to this parameter lambda. So the reason to consider these particular combinations of four derivatives is due to the fact that if you try to repeat this argument more properly, you will find particular correlation functions of four operators in n equal to 4, but crucially integrated over the space-time insertion points. So this is why these objects are usually called integrated correlation functions. There is some beautiful mathematics going on for the correlation functions themselves. Those are so much harder to study, as many of you know. But these objects are still going to be interesting. Again, from a physics point of view, what these objects are doing for you, they're producing a certain average over the space-time insertion points of the correlation function that we want to study. Again, to connect a little bit to what I said at the beginning in terms of words, these particular combinations of derivatives bring down correlation functions of which eventually in the dual theory corresponds to scattering of two gravitons into two gravitons. This object in here is a little bit more interesting. From the holographic point of view, a Wilson line corresponds to the insertion of a string. So this object in here is corresponding to a scattering of two gravitons off of a string in AdS CFT. So to quote the results of the literature, Bender, Chester, Pouffou, and Chester and Pouffou have shown that, okay, so just in terms of nomenclature, I'm going to call this one the first integrated correlator, this one the second integrated correlator, just because I studied this one first and this one second. And they also came first and second in the literature. So they've shown that these quantities, Cn tau and Hn tau, correspond to some 4-point scattering amplitudes of gravitons. Now, why 4 points? Well, you see in here, I'm taking four derivatives. Using my very hand-wavy argument of this path integral formulation, I'm bringing down four operators. Now, the whole thing is, well, okay, what type of operators? That's the result. In particular, well, this is true when later I'm going to be discussing n much, much greater than 1. The second quantity, which is also very interesting, although I'm afraid, yes, please. Very good, excellent. It's hidden in the choice of derivatives over there. I can give you more details in the Q&A, but since you know, so you write the microscopic Lagrange of n equal to 4, and you check, let's do m. What does m multiply? Well, you know very well. M is dimension 2, so it multiplies the unique operator of dimension 2, which is O2. What you have to do, you need to write the microscopic Lagrangian, take those derivatives, use the superconformal word identities, and derive the integrated correlators. I can give you more details later on. Yeah. Yeah. Yeah, no, so it's hidden in the choice of derivatives in here. So you could ask, is this the only choice of derivatives? No, it's not. There are other choices, but I'll tell you more later if you're interested, Michele. This other object, IW, which unfortunately I'm not going to tell you much about it. It is a 2-point function in the background of a Wilson line. Yeah, very good. Then I'm going to say something. Yeah. let me erase here. I want to keep everything. All right, let's erase this one. So this IW, instead, thanks to the work of Ufu, Rodriguez, and Wang, and then after that, the Italian gang of Billot, Rao, Albagno, and Lerda. They've shown that this object IW is really, as David was saying, is a two-point function in the presence of a Wilson line, which is perhaps the easiest example of what is called a line defect operator. Very integrated, again, integrated two-point function. Again, from a holographic point of view, at large n, these mass derivatives bring down two operators which correspond to gravitons. This Wilson line corresponds to a string. So this object is telling you what's happening to the scattering of two gravitons off of a string state. This is the two graviton scattering of a fundamental string. Yeah. So in these lectures, again, I want this one. In these lectures, I'm only going to be focusing on these two quantities for the following reason. Let's go back to what I said before about this electromagnetic duality. All right, well, I will have to erase this one. But I'm expecting all of you to have taken notes, so you know exactly what I'm going to be writing next. Oh, no, don't worry, Dolly. Thank you. So as a consequence, of electromagnetic duality of n equal to 4, these quantities that I'm defining here via the matrix model satisfy the following. So for any number of color, and for every SL to Z matrix, they are modular invariant functions. Yeah, sure. It's trivial actually. For n equal to 0 and 1, the matrix model reduces to 0. So those are also modular invariant functions. They're just a little bit silly. Yeah. Good. And gamma tau is the same as I wrote before. I don't think this is needed with this audience, but good.
We have
Yeah.
some statement, any n,
Yeah.
even though the relationship to the
Mhm.
physics is only a proof limit of large.
Good question.
So you're looking at something more general.
Yeah, so from the point of view of this n equal to 4 theory, you don't need to take n large. N equal to 2 is perfectly well. And actually, I'm going to give you exact expressions for any n, at least for this object in here, C. Yeah. So at finite n, that expression, actually for any n, that expression is going to be given by a lattice sum, which is completely not obvious from the matrix model I wrote before. In the matrix model I wrote before, there was no lattice sum to begin with. But n equal to 4 leaves, like, it's perfectly well-defined theory for any number of colors. What I was saying before, when I take n to infinity, is only to connect with the dual string side. So we're going to see that when we do this transition from finite n to large n, although I'm going to give you one integral representation, it's actually going to change fairly dramatically. And just to anticipate a little bit, when we're going to be taking the large n limit, this object in here will be expressible as a power series in 1 over n, whose coefficients are going to be real analytic Eisenstein series with half integer index. While instead of finite n, it's just going to be given by a lattice sum. Yeah. The connection with string theory only happens at large n, but n equal to 4 is perfectly valid for any number of colors. Yeah. The question is, what do you want to do with n equal to 4 in SU2 gauge group? Yeah. But like,
This is more interesting.
agreed. Yeah. And I was going to say also the following. So people in these audience have studied these correlation functions in n equal to 4 for any number of colors. And the problem is that it's so much harder than what I'm going to say here. So I believe in particular, we only know the correlator up to 5 loops. If you take this correlator, the full correlator for SU2 n equal to 4, and you integrate it against this measure I didn't talk about, you will actually get precisely this object in here. Yeah. And something pretty magical is going to happen. So again, spoiler. In the perturbative expansion, so what you actually would compute from Diagrammatica, the first integrated correlator will only produce single zeta values, single odd zeta values. The second integrated correlator will only produce at most product of 2 odd zeta values for n equal to 2, for SU2. Yeah. Nobody expects the full correlator to have this property. Yeah. But somehow in here you're projecting onto something magical. Yeah. So the problem is that, you see, for finite n, we know fairly little from the n equal to 4 side on the correlator. At infinite n, we also have string theory to aid. Yeah. But what I'm going to be saying, at least for the first integrated correlator, is going to be valid to any n. For the second correlator, although we have some inspired guess of what the finite n formula should be, we actually do not know it at finite n. We only know at infinite n. So that's going to be the third lecture. Yeah, thank you. Good. So let me conclude with a couple of words about this defect correlator, because that's also very interesting, and I know a little bit about it, but not a huge lot in terms of modular forms point of view. How am I doing with time, Ollie? I think this is the last thing I can say before.
More or less half an hour.
Oh, fantastic. That's great. Perfect. Yeah, absolutely. No, I just want to make a comment about this object in here, because this is the guy I'm not going to be talking about. But since I believe this object will give rise to real analytic Jacobi forms, I thought it would be nice to mention. Yeah. So the point of this last integrated correlator is that it involves what is called a line defect. So the easiest line defects in n equal to 4. Very good. Yeah. So this one are smooth line defects. Yeah. You can also compute the one which have a cusp anomalous dimension. Yeah. Actually, that's a good question. I'm not sure if there is a localization formula for that one. I want to say no. So the only way I know I worked on, so that's probably not the only way. But the only way I know that people have tried to compute the Kasparov dimension n equal to 4 is by going directly to large n in the 't limit, where you have some integrability. Yeah. But in here, I don't want to do that. I really want to keep finite tau, because there's going to be some interesting modular structure. Yeah. And that's a good point. Thank you. Yeah. So in n equal to 4, these objects are parameterized by two coprime integers, p and q. For the physicist, this is the electric charge of the defect, and this is the magnetic charge of the defect. Bunch of words. The defect with electric charge 1 and magnetic charge 0 is called a Wilson line. Not unthinkable, you're inserting the path integral, the word line of an electrically charged object. That is literally what a Wilson line is. PQ equal to 0, 1, that is called a 't line. That's a little bit harder to implement from a path integral point of view, but again, you could think of inserting the word line of a monopole in the path integral. Now, let me go back to the comment about n equal to 4 electromagnetic duality. As I said before, this is a duality that relates n equal to 4 with coupling constant tau, gauge group SUN. But now I also want to discuss this sort of object, so I also need to tell you what the charges are for a defect. And the electric duality tells me that if I change the coupling constant tau in the usual fashion, gamma tau, the gauge group, let's say again, is L of SUN. But I also need to change the charges. I also need to perform a transformation on the charges of the defect. If I do all of these mappings, the two quantities should be the same. Correlation functions of objects in here should be equal to a correlation functions of objects in there. But now let me note the following trivial statement, which relates to this Wilson line object. So for example, if I consider what is called S-duality, is the particular SL to Z matrix, 0, 1, minus 1, 0. Little exercise for the students, although that's very silly. Under this transformation, tau goes into minus 1 over tau. But importantly, if I start with a Wilson line, so something with PQ equal to 1, 0, if I do this transformation, it gets mapped into 0, 1, which is a 't line defect. So this tells me that there is some different structure in here. The two objects I'm going to be considering are going to be real analytic modular invariant functions with respect to SL to Z. When you consider line defects, there will have to be some sort of covariant object. And the reason is that if I start with this Wilson loop in SUN and coupling constant tau, it should be equal to the toothed loop coupling constant n minus 1 over tau. So we are really changing here the type of object we consider. Rather than, if you want, you can think of it as vector valued. Yeah, so what you should really be defining, you should be defining a PQ line defect. And then this transforms covariantly. But actually, I think it's better to think of this as being the Fourier modes of some real Jacobi form. So if you do like in your relativity case, you introduce some zeta parameters and use comoving coordinate, and you do the sum over all the defects, you can actually show that it must be a real analytic Jacobi form of weight 0. Yeah. Again, I'm not going to say anything, but I'm happy to tell you more. This is what I also asked you in Munich a couple of summers ago. So we studied with Concau Wen and his PhD students. We studied again the matrix model formulation of Festoon, and we derived from it a conjectural lattice sum representation for these objects. For SU2, SU3, and SU infinity. And those objects over there, they're given by some lattice sum very similar to your Kronecker-Eisenstein series, but they're not quite the same. Yeah. Yes, please.
So coming back to physics.
Yeah, very good.
Forgetting about theta.
Yeah.
Small coupling is large imaginary.
Yes, absolutely.
And now you're inverting it. So
Tooth loop in the strong coupling limit. Yeah.
strong coupling.
Yeah. So one thing that I showed, so first we gave this conjectural expression that transformed nicely in terms of SL to Z. But we had no way to check it because nobody knows how to compute the tooth loop, not even at weak coupling, actually. However, there is a really nice paper by Gomis, Festoon, and Okuda, who provided a matrix model formulation for the tooth loop. And so what I did, I used this matrix model formulation to compute the tooth loop integrated correlator, and I checked that it's consistent with this conjectural expression. If someone was able to give me the 2-point function that you were saying before in the background of the tooth loop, I would also be able to perform this integral over the insertion point to check against these results, but nobody knows that, yeah. The tooth loop correlator is so much harder to study because for the Wilson loop, you know what to insert in the path integral. It's literally the path order exponential of the gauge field. For the tooth loop, you need to insert some singular boundary condition. You give me the word line of your monopole, and you want the gauge fields to have a non-trivial monodromy around the Wilson line, has to produce the magnetic flux responsible for the magnetic monopole insertion. So you're not inserting, say that you wanted to put it on a lattice, you're not inserting any local operator, you're prescribing boundary conditions along the Wilson loop of the monopole. So much harder to implement in practice, yeah. Actually, I do not know if there are results. Already for the Wilson loop insertions, the result in n equal to 4 for the correlator are so much sparser. Yeah. But you're absolutely right. This duality changes the correlator. I'm giving you two different quantities to compute. And also changes, importantly, weak coupling on one side, strong coupling on the other side. Yeah. But luckily, at least for SU2, there is this localization results I was mentioning. In principle, that localization result is valid for all n. There is a big difference between doing something in principle and doing it in practice. So in practice, we only know it for SU2. Yeah. Good? Excellent. So this is the end of my somewhat longer introduction. What I'm going to be doing in the next lectures is studying these two objects. But I think, so I would like to start now with object number 1, but perhaps it's better to pause for more questions.
Maybe
yeah.
one question about the menu.
Mm-hmm.
You highlight the gravity
Yeah.
opposed to the massive.
Very good.
Resonances.
Yeah.
Do you have a kind of rule of thumb how I find the rule to a massive string?
Excellent question. Yes, that you should ask Michele, since you're in Uppsala now, right? You're paying him, so he should tell you everything. Yes, so that's a very good question. There's a big zoo of states that you may wish to consider. So perhaps the easiest state that you wish to consider are the higher Kaluza-Klein modes on the phi sphere. just because, again, you're on AdS5 process 5, the graviton is the lowest of such states. However, there is an infinite tower of what they're called single particle states. From a matrix model point of view, it's not super hard to see what you should do in principle. The graviton state, roughly speaking, correspond to inserting in the matrix model trace of pi square, which corresponds, just in terms of integration variable, inserting a squared. First thing you could try to do, let me try to insert a to the p. This doesn't quite do the trick, but morally, it's what you're trying to do. You're trying to insert a state on the type sphere that is corresponding to a higher Kaluza-Klein mode. You can start by inserting AP, and then you need to do some Gram-Schmidt orthogonalization. So this is something that you can compute. You can compute the scattering of two gravitons going into two higher Kaluza-Klein modes. Then over there is a whole zoo of things that you can consider. So once you have these Kaluza-Klein modes, these Kaluza-Klein modes correspond to holographically, they're really single particle states. So it really is considering the scattering of two gravitons into two higher P charge states. But these are not the only states you have. You can try to insert states whose dimension scales with the number of color. And over there, you have a lot of possibilities. So you can insert what are called giant gravitons. Giant gravitons, from a matrix model point of view, correspond to inserting the determinant of this matrix A. Clearly, since A are n by n matrices, the determinant scales with n. So it's a little bit harder to implement, but you can still do it. And holographically, these objects are corresponding to an insertion of D3 branes in the holographic pictures. This giant graviton story, there's two types of half BPS branes that you can insert. One on the 5 sphere, on a given equator, so not an equator, a parallel, and another one, which is called the dual giant graviton, somewhere in the AdS space. Then you can do even more. So this is something that we've done recently with Francesco Aprile. You can insert states whose dimension scales with n squared. So these states will actually change the background geometry. When you insert giant gravitons, you do not change the background geometry. Still AdS5 process 5, you have just inserted a D-brane somewhere. Of course, it's going to change the correlator. It has a lot of interesting properties, but it's not going to change the background. But if you insert a state whose scaling dimension is n squared, you do change the geometry. And some of these states you can generate by considering coherent states of gravitons, something like e to the alpha graviton. Then what we have done, we have given a prescription from the matrix model point of view. This corresponds to the scattering of two gravitons in this modified background. This modified background corresponds to one of these particular LLM geometries. So we did a calculation, well, Francesco already did the calculation with Rodolfo Russo and, thank you, Stefano Giusto. And they computed the graviton propagator in this LLM geometry. We integrated this integrated version, and we found exactly the same object, but we also gave prediction for basically, we gave a conjectural expression for the integrated version of Virasoro-Shapiro in this LLM geometry. Yeah. So there's quite a few things you can consider in here. Again, from the matrix model point of view, one of the downsides is that you're never really getting the correlator. You're always getting some average version of the correlator. Yeah. Yes, please. Yeah. Absolutely. Very good question. Yeah. So these are the technicalities I was sweeping under the carpet. So when you insert a trace of a to the fourth, that's a mixture of those two states, O4 and O2, 2.
Because
That's fine. For me, the graviton is p equal to 2, and there is no mixture there. So over there is no ambiguity. The ambiguity, you're absolutely right. For p equal to 4, there are two different states over there. And now you need to prescribe. So, yeah. Then what do you, the higher graviton, the higher Kaluza-Klein mode.
I mean, for me, the graviton is all.
Okay, because you're thinking in 10 dimension. Okay, very good. No, for me the graviton is O2. Yeah, very good, perfect. Yeah. No, you're absolutely right. So how is the single particle state defined? It's defined as being orthogonal to all lower particle states. So this leads to this Gram-Schmidt orthogonalization procedure I was telling you about. You write an abstract, a general linear combination of trace A4 plus trace A square square plus trace A square, and you impose this to be orthogonal to the graviton and the O3. Yeah, and then you keep on repeating it. So this is in a couple of papers by Zonkao and collaborators and Eric. No, very good, very good. Yeah, I know you did that, absolutely.
My question was another one, but maybe we can.
I'm very happy to pause now because then the next I will describe this object in here in more detail. Yeah. Very good question. Yeah. So from a matrix model point, so okay, those combination of derivatives. First of all, you can ask yourself, okay, what is the most general combination of derivative I can take to get 4-point functions? So besides n, tau. Oh, I have space over there. Very good. Very good. What are the parameters of the theory for which you still have localization? Because at the end of the day, I want to get a matrix model and take derivative of a matrix model to compute an actual function. Okay, besides the number of color n, you have tau, you have the mass parameter n, you have the squashing parameter b, but actually we have not really played a lot with that. You consider the theory not quite on S4, but on an ellipsoid deformed by this squashing parameter b. Again, since the squashing is done via the stress energy tensor, you could still expect that taking derivative with respect to b will bring down some stress tensor, which is in the same multiplet as O2. So this is also to your disposal. But then,
I'm sorry.
yeah. I did not, exactly, because it was not necessary for me. Yeah, I'm just telling Michele. So there's a bigger matrix model, a more general matrix model that you can introduce. The one-loop determinant changes. Instead of having this Barnes G function, you introduce this upsilon B function, which is given by some infinite product of gamma functions. But you can define a matrix model for this n equal to 2 star theory on a different background. This background has yet another parameter b, which is some real positive parameter. And basically, the squashing is something like b plus b inverse, something like that. So you can define yet a bigger set of observables. B equal to 1, this ellipsoid reduces to the 4th sphere. The reason why there was no b in my lecture is because I implicitly set b equal to 1. But if you want to ask yourself, what is the whole set of observables I could try to obtain in this way, then you also can introduce this deformation. Yeah. One second. And then there is another parameter, tau p, which corresponds to higher operator insertions. So I can write the dependence of tau p fairly quickly, because it does not affect the one-loop determinant. It affects Nekrasov, and actually this is something that we don't know. We do not know Nekrasov for general. We do not know Nekrasov for general B, but we don't know Nekrasov for this general tau p that I'm going to write in a second. But to answer your question, this tau p will do the trick. So, let me not do this b. I'm going to set b to 1 because it's not necessary from what I'm about to say, but just keep it in mind. You can also do that. So you can write a more general action, a more general path integral, which is a function of n, m, tau, and tau p, with p is greater or equal than 3. And the path integral, actually the matrix model integral, is identical to what I wrote before. That perturbative, completely unchanged. That Nekrasov has changed a little bit. But the important thing is this one. Let me now write it explicitly. It's 2 pi tau 2 a squared, trace of a squared, plus the sum, p greater or equal than 3 tau p trace of a to the p. Now, by taking derivative with respect to tau p, you can bring down this trace of AP. And now you can try to ask what I was saying before. You can ask yourself, okay, this is going to bring down some A to the P, which corresponds to an admixture of gravitons. Can I find a combination of derivative with respect to tau p, for p equal to 2, 3, 4, and so on, such that this combination is perpendicular to all the lower Kaluza-Klein modes? And the answer is yes. And then in this way, you can consider the correlator of O2, O2, OP, single particle states. Yeah. Now, why the measure comes as it is in this paper I was mentioning about by Zonkao and friends and Eric Permuter and friends. Yeah. But the fact is that you can introduce this deformation. Yeah. It does not modify the one-loop determinant, but it does modify the Nekrasov partition function. So in particular, we have some conjectural expression for the one instanton Nekrasov in this tau p generic, but it's not known for generic instantons. Yeah. And then you can do some checks against your results from holography. Yeah. You can insert some higher p. And then you can play with what I was saying before. You can now try to insert some p at large p, but then it depends what you insert. So what we studied recently with Francesco and my former student Rudolf, we studied O2 to some large power, but this is not a single particle state, as you know very well. But then you can also check the differences with the single particle states, because you can also obtain the single particle state. If you take p to be large and scaling with n, this corresponds to the Driveran insertion. Yeah. Good. So, is there a coffee break after the lecture, or perfect? Pretty good. Perfect. Then it's a good point to stop. No, because then I'm gonna start talking about this first integrated correlator.
I think we should start clapping you.
Thank you.